done by the 31st of December. You need 24. And then we're doing current NCSEA webinars through SEAAK. It's sponsored as part of your membership here. So our next one's on Thursday. Reach out to LaToya Watson at Reed Milton if you'd like to RSVP. AELS updates, Erling.
Yeah, the ALS board is continuing on their regular meeting quarterly, but the governor has a regulation or an executive order in place that says there's no travel and no new regulations to be formed. So at the moment, can't really do much. Some of the regulations we worked on, like the one changing the SE definition for bridges, are stuck in bureaucratic morass. So nothing's changed on that yet. The big change for the board from last year was the bill was approved by the House and Senate to add interior designers as a profession in Alaska, add them to the board. Last I'd heard, that bill had gone to the governor, but hasn't been signed yet. One of the biggest things for all of you that you're interested in, though, is it is renewal season. If you haven't yet, keep in mind you'll be coming up on BE renewal at the end of the year. Continuing education regulations have changed significantly since the last time around. The overall number is the same, but you can no longer carry over hours from last year to this year. If you're counting on that, don't. The good news is that there's a new option for what's called structured self-study, which is anything we do in our profession that adds to education, like learning a new software, watching a YouTube video on HSS Connections, something like that. You can do it on your own, and you can fill out a form. You could get up to, I believe, 4 hours a year or 8 hours total for the renewal cycle. So a lot of the stuff that we do that hasn't counted in the past now can count. Info for that and all the forums are on the AELS website. If you have any questions, reach out.
Right, and with that, Magda, we're going to do the treasurer's.
Can I add one thing on that?
Yes, sir.
That form that you can list your CEUs, I highly encourage you to go get it and start filling it out. Don't send it in, because we get every 2 years, probably a half a dozen to a dozen licensees who've sworn they have 24 hours of continuing ed. And then when they get audited, they don't. And so they go straight to the paralegal and to fines, and it's fraud and perjury and all that kind of stuff. So if you want to make sure you got enough hours, you want to make sure you got enough hours before you sign that you have. If you just, well, I think I do, oftentimes you don't. And that will get you in more trouble than saying that you don't and asking for more time.
Thank you, Colin. All right, treasurer's report, Magda.
We have $16,227.23 in a bank account. That's not counting for activity right now. We most likely we're gonna have one more expense for the PO box, and otherwise, since the last our May meeting, our activities mainly were for the lunch expenses and then the payments. Also, we had website domain fee that we went through, and expenses that were associated with sending with Nikolai attending the National Council of Control Engineers.
Leadership Summit in,
Yes.
I think it was in May, I believe. All right, with that, we'll introduce our speaker. So Ted Goldstein works with Atlas 2. I became aware of him from listening to a structural engineering podcast. It sounded really cool, and then I saw him on LinkedIn. So I reached out, asked him if he could come present. A few years ago, me and Sterling and a bunch of people in the oil and gas industry were having a hard time with people welding nuts for lifting lugs where we couldn't really reach them. We went back and forth, and then it's kind of funny because one of the ideas that we were throwing around in the room, Ted Goldstein actually invented. So it's a real thing now. They don't have it for low temperature steel. Pretty cool progress. And he had a pretty cool story on the podcast I listened to. So with that, Ted, I'm going to hand it off to you. Go ahead and share your screen and have at it.
All right, perfect. Yeah, thank you so much, Nicola. I appreciate you setting this up. And as you described, this is to a certain extent based on the stuff we were talking about on that structural engineering podcast. So it's a little different from some of the presentations you might normally get. A little more narrative here. But I hope the first portion where we're going to kind of talk about how that came about, hope that'll be interesting for you guys. And then the second portion, maybe 2/3 of it, we'll talk a little bit about the Shuriken, the product that Nikolai mentioned, and then also some other things we're doing to try to ease HSS Connections. So a bit of an outline. I kind of gave it away already. First, we'll talk about the shock, the stuff that happened to kind of get the ball rolling on this, and then my quixotic quest to change structural engineering in the US, and talk a little about Shuriken itself, how it works, things you can use it for, that sort of thing. And then we're going to talk about some software that we've been developing at Atlas to try to make HSS connections easier. So essentially, the second two parts are the physical things we're doing to try to make it easier, and then the intangible stuff that we're doing to try to make it easier for the engineer when you're working on HSS connections. So with that, I'll kind of jump into it. We'll start with the shock. So for to set the scene, for several years I had been working as a consulting engineer in New York, mostly working on buildings. And around 2018, my wife got a job opportunity over in Japan, and we decided to go over there for it. I did, when I was putting together this presentation, I thought, I'd add a little background slide there just to set the scene. So I asked AI to make me an image of flying to Japan, and I can announce that, I think our jobs are safe for now. But in truth, it was kind of, I wasn't too thrilled with it at the time. Between licensure and language, it seemed like I was going to be, an unemployed structural engineer for the foreseeable future. It was a bit bittersweet, but it turned out to be a really eye-opening experience. When I was working, and I think this is true of a lot of people and a lot of, doing a lot of work, you kind of assume that the stuff you're seeing, you've been doing it for a while, you've seen it all. And so specifically in this case, I assumed that since concrete is the same and steel is the same in Japan, then structural engineering is also going to be the same. And that turned out not to be the case. So I'm going to throw up a few images here just of some interesting structures, just to kind of set the scene about, really how different it can be. Here, for example, is, big old moment connection for at a major rail station. Obviously very different than we would go about doing something like that here. They've got all of these diaphragm plates cutting through each other at every height of every beam going into the column. A lot of round columns, also something we don't really see in the US very much. Here we've got some double BRBFs. Again, this is at a large train station, going very steeply up to a moment frame supporting the roof, very different from anything I had seen at the time. This is a high-rise that's actually completely precast. So I should say, the joints are poured in place, but all of the structural members are precast, which is a system that had never even occurred to me before. It's not really relevant to where we're going with this presentation, but it's so interesting I did want to include it. If we kind of zoom in on what those elements look like, you've got these monster blocks of concrete that get trucked in, and you can see they have the dowels sticking out that are going to allow them to splice with their neighbors. So this piece that we're looking at here, the rebar that's sticking out to the left is basically at the bottom of this column. It's going to be dropped into sleeves and grouted solid with the column below it. And then you have all the beam connection points with these big couplers right, where they're going to couple the various members together and then pour the joint solid in place. So totally different than anything I'd ever seen in the U.S. You know, steel is the same, concrete is the same, physics is the same, but that doesn't mean people are going to do things the same way. And it's actually funny, in this particular example, I spoke to a Japanese structural engineer who explained to me that this was often something that gets done as a value engineering option for buildings, which to me was hard to even believe, right? The idea that this would be the cheaper way to do things, but of course, economics are different in different places. So very eye-opening experience in that regard. Just a few more examples of stuff we don't usually see here. Here's a seismic retrofit of a mid-rise office building. Obviously, very unusual geometry. They had to get around that door. But aside from the kind of the geometry itself, that there's you know, a theme here that we see a lot when it comes to structural engineering over there, which is that in the U.S. we tend to fabricate the members and then we create the joint in the field. You know, we'll attach a porch plates or whatever we have to, but generally the point where things come together in the field is where one member meets another. In Japan, it's very common to fabricate the joint in the shop. So in this case, right, you've got that large rectangular plate in the center of this. That's fabricated in the shop, and you know, with stubs in all direction, and then they splice in the field. So, right, we do members and joints in the field. They do joints and splices in the field. Not 100% of the time, but it's a very common feature there that you very rarely see in the U.S. So again, just, you know, different ways to solve the same problem. You know, eye-opening experience in that regard. Here are some very large hollow box girders with, you know, varying kind of smooth transitions. Again, another infrastructure project. Nothing, I mean, this is, we of course do box girders in the US, but there's sometimes a certain just aesthetic to it. It certainly looks very different from the things you tend to see here. Here's another example of detail that never really crossed my mind. They tend to use, as I say, a lot more round columns and a lot more box beams. So what happens when you need to moment connect a box beam to a round column? This is it. And it's actually a very common detail over there. Something that I'd never really thought about. When you do think about it, right? The forces all work, of course. I mean, it's thoroughly engineered, but it's just, you know, a reminder of you know, how much we tend to focus on the ways of doing things that we're used to, as opposed to you know, off the whole universe of possible solutions to a given problem. And then I threw this one in, not because it's terribly representative of any particular aspect of design and engineering over there, but because, you know, nonetheless it had a certain je ne sais quoi to it. I can't imagine ever seeing a connection like this done this way in the US. When you really step back and look at what they were trying to do, there is a certain method to this madness, but it's a very different madness than we would probably put into place here in the US. So really, you know, seeing all this, you know, definitely gets the imagination, gets you thinking about things in a way that when maybe, you know, at the time I'd been working about 8 years, you know, sort of tempting to start to think you'd seen it all, and clearly you hadn't. Now, all the stuff I've been showing for the most part so far is, I mean, there's the retrofit there on the left, but for the most part, infrastructure, just because that is where things tend to be left open to view, and so it's easiest to see structures and really you know, compare things there. But my background is in buildings, and so, you know, that's no less interesting place to examine, and that's what we're going to look at for most of the time. So when we look at steel buildings over in Japan, we see a couple of really common themes that are very different from the US. So on the left here, a very small building, at most 15 feet wide, on a very narrow lot in Tokyo. On the right, also in Tokyo, we have one of the largest high rises in the city. Since this was taken in, I think, 2023, this has been completed. Before I get into the structural engineering, I do think there are some interesting things to point out. First of all, on that image on the right near the bottom, you see that skewed pyramid. That's actually the national sumo arena. So you're in the heart of Tokyo here. A lot of you know, cultural stuff mixed in with the modern high rise and what have you, which is a very cool aspect of the city. But then also just in the terms of the way they build things, I mean, you know, in the US, we build a high rise, you might see a couple, maybe 2 cranes on the side of the building max. Here, when I went ahead and attempted to count, I got to 34 cranes. So just, you know, different way of doing things. You wouldn't typically see that on many American construction sites. But with that in mind, you know, looking at the engineering, even though these 2 buildings are obviously at a very different scale, there are a lot of similarities between them in the way that they're designed to, you know, take specifically lateral forces and bring them down to the foundation. And the biggest key is that neither of these buildings has a core. That's obviously going to be the case for the one on the left because there's simply no place, you know, there's not enough space to put a core. We wouldn't do that either, but for an American engineer to see a high rise like the one on the right without any kind of centralized lateral resisting system is very unusual. Of course, they have a core in the center in terms of having a place where the elevators are located and the stairs, but they don't concentrate the structural system around that vertical transportation. Instead, what we see in both of these buildings, at admittedly very different scales, are distributed moment frames. And so on the left, there's just a close-up from the building that we're looking at there. And this is very typical of Japanese steel construction. Basically, we've got diaphragm plates. They cut the column into multiple pieces during fabrication. They insert a diaphragm that coincides with the flange of each steel beam. And then they attach stubs to those. And they, again, talking about fabricating the joint and splicing in the field. If we look at the larger picture, you can see all of the beams. They have those stubs that are fabricated in the shop attached to the column. And then in the field, they're not really making what we would think of as a shear connection or a moment connection. It's actually, you know, a beam splice. So that's this is basically universal in steel construction in Japan. Every column connected to every beam at every level, and that's lateral system. For the building on the right, because of the state of completion it was in, I don't have a great shot of one of those joints specifically, but here's another example of another column from a high-rise project, maybe not quite as large as this one. But again, we got, you know, an HSS column. When they get very big, they go to built-up boxes, but almost always square and hollow. And they've gone ahead and they've, again, cut that column into multiple pieces in order to slide diaphragms into them, re-weld the column, attach the stubs, and then they're going to go ahead and splice that, splice those stubs to beams in the field. So with that, let's look a little bit about, you know, kind of compare this with what we tend to do in the US. So in Japan, we've got distributed lateral systems where basically every member is taking part, or excuse me, every column is taking part in the lateral system, and indeed every beam that is on a column line is part of it as well, which basically means there are no gravity columns, just very unusual from an American perspective. And that means that because you're distributing load over so many more connections, that you tend to have more but smaller lateral connections from beam to column. Now, this is kind of in a relative sense. The seismic loads in Japan are practically off the charts, so the connections may not actually be that much smaller than we're used to seeing in the US. Of course, Alaska obviously has very high seismicity as well, but from a kind of national engineering community standpoint, you know, they tend to have larger forces. And then the last thing is, of course, these frames are biaxial, right? Every column is not only participating, but it's participating in both the X and the Y directions. In the US, on the other hand, we tend to have concentrated lateral systems. So whether that's a core in a high rise, maybe some outrigger trusses, but again, you know, concentrating that function of moving the overturning moment out to the perimeter of the building, or in our shorter buildings, right, we tend to want to keep our lateral systems on the edges. Usually the idea is to reduce the effect of accidental torsion. These are certainly, I should say, these are obviously generalizations. There are plenty of buildings where this is not true, but more often than not, this is what we tend to see in the US. And then as a result of that, of course, we have a lot of gravity columns in our buildings that are not participating in resisting lateral loads. That means that the fewer connections that we do have tend to be resisting more force. And we tend to separate X and Y, right? So we'll have a frame that does one direction, and we'll have frames do the other direction, but generally speaking, they don't necessarily interact. Again, bit of a generalization here. If you do have a core and high rise, obviously that's acting as a tube. It's going to take force in both directions. So that last bullet point is, to a certain extent, tends to be more applicable to shorter buildings, but it is a characteristic we see often. So, okay, we've got these two very different ways of approaching basically the same problem. Make a steel building that doesn't fall down when you push it sideways, right? And so, there are a couple ways you can look at this. I mean, maybe the simplistic way is to say, well, they're doing it wrong. That's not really terribly satisfying. Plenty of smart people over there. The other way, equally unsatisfying, especially sitting in our seats, is we're doing it wrong, and you too, Hawaii. But that is equally unsatisfying, I think. And I think in reality, the answer is that these are two different approaches to a similar problem. And I think there's a good chance that both approaches have a time and a place when they're the most efficient way to do something. And that in both countries, people have a tendency to stick with what they're used to, rather than kind of looking at things with a more open mind at the early stages of a project, right? Which is when this kind of comparison would have to happen. So when I was looking at this, I think I really kind of focused on these, mid-rise or lower rise buildings where we do tend to separate our X and our Y lateral systems. And in those specific cases, it seemed like there was actually a pretty strong argument that the Japanese approach would allow you to reduce the tonnage. Now, of course, it comes with more connections, so cost is obviously a much more complex thing than tonnage. But to the extent that there are a lot of projects now, increasing number where sustainability is concerned, the best thing you can do to reduce the impact of a project is to reduce the amount of stuff you use. So that's what kind of got me, focused on this approach and really started what I'm calling the quixotic quest to get it to see wider adoption in the U.S. So just to illustrate this point, I want to kind of look at a conceptual building here. This is very much qualitative, and as I say, conceptual. It is inherently oversimplified as I go through this. Really, just an attempt to try to describe things in a graphical way. So, am I missing some details? Absolutely. But I do hope that by running through this, I'll be able to kind of get across the way that I was thinking at it at the time, at least, for better or worse. So we can imagine, what if we designed a building? Imagine this is, say, a 5 to 10 story building with it's got this very regular grid. Of course, when you're doing a conceptual example, you don't have to worry about people getting between floors and assume everything's perfectly regular. And we can say that for now we're designing it for gravity only. So if we design for gravity only, then the footing size and the column size are going to be relatively proportional, right? They're both, the tonnage in the column and the area of the footing are both going to be relatively in line with one another. And so we can kind of use that as we look at this as a graphical tool for understanding, how much capacity we have and how much material. So I'm kind of treating the footing size here as a graphical representation of not only the foundations, but also of the material that's in the columns. Now, if we design this for purely gravity load, as I say, then we're going to be governed, these footing designs and and the frame design are going to be governed by the 1.2 dead plus 1.6 live combination in LRFD. And of course, the interior columns are going to be the biggest because they're picking up the most floor area, slightly smaller at the perimeter where you've got half the floor area plus some facade. And then, of course, the columns at the corners are going to be the smallest with the smallest floor area, but they do have the same amount of facade as the perimeter columns. So we've gone ahead, we've designed it for pure gravity loads. If we were to now look at the lateral load combination, I'm going to say the wind load combination, but it really doesn't matter whether it's wind or seismic. It's just I put wind here because wind happens everywhere, but seismic does not really. But if, before we've applied any lateral loads to this structure, we were to look at that lateral load combination, the live load factor has gone down from 1.6 to 1.0. The wind load doesn't exist yet. And so what that means is that all of these elements, the columns, the foundations, and the structure, are now loaded below 100% utilization, right? So those, as kind of aqua color there, is meant to illustrate, again, very qualitatively, the amount of capacity that you're actually using in these columns and foundations. And we can see, if the sign is the utilized capacity, that means that we have some extra capacity in white. So now if we go ahead and say, okay, we're going to start applying some lateral loads to this, let's produce a lateral system, we can go ahead and moment connect all the columns. I'm going to look at the distributed approach, what they do in Japan first, because it's a little bit simpler. But we can imagine, if we started with 0 lateral load and then we start to apply it gradually, like get someone to, walk up to the side and start pushing on it. When those loads are very small, we're not actually going to have to do anything beyond make the connections to resist them, right? Nothing needs to be upsized. We don't need to add any material to the system because all of these foundations and all of the columns and indeed the beams as well are going to have some extra capacity from the fact that we have that lower factor on the live load. And we can kind of look at this graphically. If we introduce a wind load, which I'm representing by this red box, again, my apologies, it is oversimplified. This is, just to get the concept across. Part of that wind load is going to be taken up by the excess capacity that we have in the columns and foundations. So if we go ahead and we take all those white rectangles from all the foundations and we kind of stack them up, we can see that's the amount of this load which is going to be addressed merely by utilizing that extra capacity. And what's left is the amount of load that we're going to have to actually add material to the system in order to resist. And the nice thing about a biaxial system is like this is that if you look at it from the X direction, you add the material you need to do, well, you've kind of automatically taken care of the Y direction. Now, naturally, this is unusually symmetrical, but the general concept is there. So that's the distributed case. If we now look at what we often do in the US, I don't know if I would even say it's a majority of the time, but it's certainly a very common thing to see buildings that are laid out something like this in the US, where you have a lateral frame on the perimeter. You've got obviously separate X and Y directions. Sometimes you'll see the corner incorporated to make the frame wider. Sometimes engineers will leave out the corner because obviously it's a little harder to resist uplift there with a smaller footing. For the sake of this, very conceptual comparison, it won't really matter. But suffice to say, if we now take this system and we go ahead and apply wind in the X direction, we are still going to have some excess capacity before we start adding material coming from those footings, but it's going to be a lot smaller than before. And so pretty soon we're going to have to start adding material to those frames in order to resist that lateral load in that direction. Similar, we can do the same thing for the Y direction. In this case, of course, it's a totally different set of columns and foundations and beams that are participating. And so we're going to need to add material to them separately. And so you've got, again, for comparison, that's the distributed system above, and then the sum of those two blocks, the discrete system that we often use in the US below. Now, again, I can't stress enough, this is oversimplified, it's qualitative, but I think it gets across the point of how using members in two directions is helpful because you don't have to build essentially two lateral systems and add the material for that. But I think the bigger thing that it highlights is how, we've got these columns in the center of the building that are picking up the most floor area. They're designed for the highest loads. And then what we often do in the US is we just ignore them. We have that excess capacity for the lateral load case, but we don't use it. And so being able to incorporate those beefy interior columns into the lateral system has benefits when it comes to the amount of material that's going into a building. I want to emphasize that just because, this is a useful system potentially in this kind of specific example that I'm bringing up, doesn't mean that it's justified to be used in practically every building the way it is in Japan. And as a case in point, I have some fun images here of when maybe it was taken a bit too far. I'm not sure that those books or that playground equipment really required them to cut the columns into pieces and put diaphragms in there and make, full capacity moment connections. But such is the allure of the familiar, right? That's how they tend to build things, and so that's how they do it. And so certainly, not suggesting that we are any more guilty of it than anyone else, but it's a normal thing to just kind of stick with what you're used to, even when there may be some better options out there. So that essentially, for better or worse, is why I kind of found myself figuring out, how do we make this system, if not a prevalent system in the U.S., certainly at least an option that people can look into when the time is right. But there is a big problem, and that is when it comes to splices. So here's another very typical construction site in Japan. We've got all the features we've seen before, the HSS columns, moment connections, every beam at every level. But here we can see, all the splices that are required in this system. And, because generally speaking, it's very difficult to bolt things together with HSS, or at least it was. These are all going to be welded splices. Now, in some parts of the US where you're in very high seismic zones, and actually I'd be curious to know what the standard practices are in Alaska. I know in California, there are locations where even if you have a wide flange column, there's a good case that good chance rather, that you're going to be welding the splices. But for the majority of the country, bolted splices are the way to go. And if you're going to say, hey, there's this great new system, but by the way, you have to weld all the splices, you're kind of likely to get laughed out of the room. And so that's what kind of got this quest, to a certain extent, that may be overstating it, but this hope to find a way to be able to utilize bolted splices at these locations so that this kind of system, the benefits that it has in certain situations, can be realized over here. So if we look at what a bolted splice for an HSS column would be, I mean, it's not so different from a wide flange. In this case, I'm showing it with splice plates on the interior. They could just as easily be on the exterior. But the nature of the problem isn't really changing, right? You don't have access to the interior of the tube, so how are you going to, get a bolt in there and get it tightened? Of course, usually we're using TC bolts, but even with a TC bolt, you might tighten it from one side, you still have to insert it from the other side. So, the challenge remains. So some basic features of what you need to achieve this. Obviously, you need to hold the nut in place, and Nikolai was talking about tack welding nuts. We're going to touch on that a little bit later. That's the most basic requirement. You have to resist torque from pre-tensioning. If you're primarily thinking about column splices, even if the code does not strictly require them to be pre-tensioned, most engineers are going to want their column splice bolts to be pre-tensioned. And you want it to work with the existing codes, right? There were already nut holders that existed, for sheet metal and automotive and things like that. But they tended to do things like, for example, have extra layers within the plies of the connection that don't really work in the structural world. And lastly, we have to allow for erection tolerance. And that is really, again, going back to that example of tack welding a nut. One of the beautiful things about bolted connections, aside from the fact that they're somewhat faster to assemble, is they've got a lot of tolerance compared to welded connections, right? And so, it's much easier for erectors to get things to fit and get those connections finalized when you have that tolerance. So with that, kind of went from the basic concept through a whole bunch of inadequate ideas. Essentially, start out with drawings, gave way to models, gave way to patent images and that sort of thing. Cast steel gave way to sheet metal. And with each iteration, you bring up new problems that you have to try to figure out how to deal with. The one up here is one of my favorites because of how ridiculous it is. The idea was to let that part in the middle move for the tolerance. But when you start putting torque on it, of course, those kind of squiggly parts will straighten out. You resist the torque. The problem is that if the person inserting the bolt pushes too hard, it's just going to move upwards and the nut will fall out. And so, each of these is an effort to address the shortcomings of the previous one, basically. So we went to two pieces, and then finally that piece in the center went from being a steel sheet metal piece to an injection molded piece just for manufacturing reasons. And at that point, I had kind of arrived at the conceptually the geometry that would eventually become Shuriken. So I'm gonna move away from the narrative now a little bit, talk a little bit about Shuriken itself. I do want to pause and just note, obviously this is a product we sell, it's a product I manage, so it's difficult for me to be 100% objective. I do think it's very useful, but I do want to acknowledge that while this is, I think, a very great tool to have in the toolbox, it is far from the only one, and it doesn't mean that it's the right choice in every situation. And I'll try to touch on that a little bit more towards the end as well. But with that out of the way, bit of an overview of Shuriken. So as we said, this is a way of making one-sided connections when you can't access the interior, specifically originally talking about column splices. Because you're just holding a standard nut, you can use standard bolts, so A325, A490 bolts. They can be fully pre-tensioned, and once they're in the field, the erector is going to be able to put things together with standard tools. So how does it work? Basically, you have it's kind of like a one-time use wrench is one of the best ways to think about it. So you kind of have a socket, like in a socket wrench, that's going to hold the nut in place in that cap in the center. The teeth in the cap interlock with these tabs in that steel ring around the outside, and then it gets tack welded down to whatever you're working on. So when you apply torque to the nut, that's going to twist the cap, and it's going to get resisted by those tack welds. And the other thing we'll talk about in a bit is how these part of that steel ring, those tabs are flexible, and that's the part of it that allows for tolerance and connection. So I'll do a brief video here just to show you how they're installed and basic connection geometry. Essentially, we're gonna hand tighten the nut and the bolt in the shop just to get the nut in the right spot, roughly the right spot over the hole. Tack weld the four corners of Shuriken, and then you can pull the bolt out. And now you're centered, adequately centered, because of the adjustability. And you can, know that it's going to be in the right place. At that point, once you've fabricated the plates, you can slide them into the tube, shop bolt one side, and then in the field, when the next portion of the column comes into place, drop it on, and you can field bolt the other side. That is in very broad strokes, how it's used. So, move on to the next slide. Okay. So configuration, just a bit of technical, get it out of the way, but so essentially we just saw kind of the left side of this image was the Shuriken getting mounted with the nut on the inside. Of course, we're fastening 2 or more plies of material, and then on the right side we have bolt. If it's a snug tight connection, the bolt is all you need. If it's going to be pre-tensioned, then we need DTI washers are strongly recommended in order to be able to verify that tension from the outside. So we talked about tacking nuts. It's one of the most common questions that comes up, so I do want to address it here kind of preemptively. A few things when we do consider taking that approach. First of all, the code is complicated. I think there's this conception that the code does not allow you to do it. It's not quite that cut and dry. If you look, for example, at Design Guide 21, I believe it is, from AISC, I think it's funny, actually, it's called like a welding primer for engineers, but it's like a 300-page primer. But they actually have a section on welding nuts and bolts, and they do give guidance where if you really had to do that, you could do it there are best practices to do it properly. The problem is that it's pretty onerous, right? You've got to preheat, but make sure it doesn't get too hot, and you need to use a particular type of electrode, and not put too much material down at once. And in the end, if people are tacking nuts in a shop, they're not going to do all this stuff. And if you don't do all this stuff, the result is you're going to get a brittle weld, right? So if you're in the field and things are not quite fitting, and that nut pops off because the welds are brittle, you're going to be in kind of a difficult situation, right? So with the Shuriken, you have that sheet metal cage, which is a much more ductile attachment. It could get deformed a little if people are particularly vigorous in getting the bolt into place, but it's not going to get knocked off. But the biggest issue is adjustability. Again, being able to make sure that you don't need things to fit perfectly together in order to get the connection to work. So in this case, just got an image here of a nut that you can see the holes are not quite perfectly aligned. The Shuriken itself is also installed a bit to one side. But in a situation like this, basically an erector can stick a spud wrench in there and just push it whichever way it needs to go. Right, so the idea here is to always have enough flexibility that regardless of which edge of the hole it was installed on or which edge of the hole the bolt is coming in, you're going to be able to thread the two together. So talk a little bit about some applications. Up until now, I've been talking all about column splices, and for the longest time, that's really all that I was thinking about, and even after Atlas 2 became involved, all that we were thinking about with product. And it feels almost silly in retrospect, because we've learned, thanks to just the inventiveness of the engineering community, of so many other ways to use it. That's almost you find yourself constantly saying, why didn't I think of that? But with that in mind, I do just want to share a few of the different ways that you can use it to a certain extent, just to get the imagination flowing. So I did talk about columns. I'll just cover this really briefly. If you're doing a column splice design, there are a few considerations. Gravity versus lateral, right? Obviously, if it is a gravity column, because let's face it, we have a lot of those in the US, you're really just designing the bolted connection to hold things in place, make sure things don't slip, right? Because the vast majority, or if not all of the load, is going to be transferred from the upper column to the bottom column through bearing. Obviously, for a lateral connection, if you have moment or even tension in the column, at that point the bolts are going to be doing much more of the work, and so you may end up with more bolts, as in the example on the right there, where we have a column that's part of the moment frame. And then the last thing is single versus double shear. We'll see in a minute. There are a lot of different ways you can go about making a splice, and there are trade-offs, in terms of how easy something is to fabricate, how much material it uses, how good it looks, etc. So we'll look at those real quickly. The basic one where I showed kind of before, the section where you have the plates on the interior, that's the single shear interior splice. That's kind of the workhorse of Shuriken splices. If you have a case where you have particularly high loads, you can do a double shear version where you have a plate on the outside as well. It's more pieces. It's a little bit more effort for the erector, because they have to get the one of the two column pieces to fit between 8 plates instead of just around 4. But you do reduce the amount of connection material, both in terms of steel, and then also, of course, you half the number of fasteners and Shuriken. So if your loads are particularly high, this is a good option. There's also a version for an exterior splice. So those first two we looked at are great for columns or maybe cantilevers, when you have a situation where you can, kind of slide a member into place along its long axis. Not so great if you have, let's say, a beam, an HSS beam, where you've got a connection at both ends and you're trying to drop it in from above. Because if you have plates sticking out, you're just not going to be able to drop it into place. So in those situations, there's configurations where here essentially we're attaching the Shuriken to a mounting plate which sits on the interior of the tube, but it doesn't actually cross the boundary, the cut line between the two tubes. That holds them in place, and then once the piece is erected, you can go ahead and bring on the splice plate from the exterior and bolt it up. And then there are a couple other approaches, big copes, and in this case we actually have kind of plates sticking out, and we cover them with some C-shaped covers. These are less common, but all of them have trade-offs in terms of how efficient they transmit forces, how what's the maximum amount of force they can handle, how complex are they to fabricate, et cetera, et cetera. So suffice to say, there are quite a few options based on the specific demands that you may have, and certainly we're happy to help out, in choosing the right one for a given project. Few extra examples there. Here, just truss webs are actually a very common situation where we have that issue, where we can't slide things together if plates are sticking out. So we can do a truss web with the exterior splice. Here's an example where they did all 4 sides. Covered splice, hook splice. I won't really go into detail here, but suffice to say, if you run into issues, there's probably a way to get around them. One other approach, which is not really a shuriken approach, but I thought it was very clever, so I figured I'd include it with the trusses, is just to go ahead and split your vertical member. So in this case, this is a pedestrian bridge truss. They've got a vertical member right at the splice, and they've got a channel on both halves of the truss that'll get bolted together through its web. So there's always alternate methods as well. Here's an example of one of those trusses. You can kind of see, if you can see my mouse, you've got the cord splices are of course just basically column splices on their sides, and then they use that exterior approach for the webs. So then this is an overpass of a very wide freeway in Texas. Beam connections, I won't go into much depth here, but again, we have a book of conceptual details, as well as actually some more kind of rigorously engineered typical details that we can share with you guys. But suffice to say, there are a lot of different ways you can go about making a shear remote connection if you don't have access. And again, it's going to be based on whether or not what the level of force is, whether there are aesthetic requirements, do you need the tube to be sealed, et cetera, et cetera. So there are different options based on what you need to achieve with the connection. One thing I will point out just on the right side here with the moment connection is we do have, again, that mounting plate that I mentioned earlier. So essentially you would put together this plate, which has, in this case, 8 shuriken on it with the nuts on the inside. It's not structural, right? It's essentially acting as a big washer. But by using 2 extra bolts, you can hold that plate in place. And then once you've slid the beam in between these, we'll call them flange plates, you can go ahead and make the actual structural connection through those plates. So just a different way of holding things in place when you can't have plates that are protruding from the member. One of probably the biggest example of why didn't I think of that moment was connections up against a wall. If you're in a tight spot and you just can't get a hand back there, sometimes it's a lot easier to just mount the nuts ahead of time and slide the beam in from the side than it is to potentially put big access holes or copes. Of course, with a moment connection, you can't put a cope. If it were a shear connection, that would be an option, but regardless, probably easier to just mount the nuts ahead of time. So it just makes that a little bit simpler. And then similarly, here's an example with a brace frame. We can't see the wall here because we're looking through it, the detailing model, but just again illustrating the concept. So with that, I'll look at some technical concerns, things that are maybe a little different from a typical bolted connection, just to keep in mind if you do have a situation where a shuriken seems like a good solution. First of all, it's a wrench, not a fastener. It is essentially means and methods. To give an example, you could imagine, if not expect, a case where if you designed a bolted connection like the one we're seeing here on the right, maybe instead of shuriken, the steel erector just wants to buy a 40-foot wrench and drop it in from the top of the column. They can do that, right? Whether you use a wrench that's attached or a wrench that has crazy long handle, it does the same job, right? So basically means and methods. We do say that engineers should spec them simply because they're not 100% known at this point. And if you draw this bolted connection without showing the shuriken, the fabricator might think you're an idiot. But we may eventually get to a point where it is understood what you would be looking for there. So with that in mind, given that it is a wrench rather than a fastener, we're using standard bolts. You can see the A490 here in the photo. RCSC and AISC requirements for bolted connections all apply, and of course you can meet all those requirements. And then the last thing is, again, while we cannot tell the engineer what to do in terms of how they go about inspecting these, we do strongly recommend DTI washers rather than using turnip nut, just because it is a verification method that can be done completely from the outside. A note, if you're ever doing anything with a fatigue consideration, the shuriken is getting mounted with tack welds, and those do create a discontinuity. That's okay if you have a static load, but if you have something with fatigue, whether that's high cycle fatigue like in a road bridge, or low cycle fatigue like in a protected zone of a seismic assembly, we want to make sure that those tack welds are not on the load carrying members. So in this case, essentially what we would do is we would mount the shuriken to a thin plate that is essentially neglected when the calculations are done. And that way, when we sandwich it with the actual splice plate that's carrying the load, the tack welds are not touching the load carrying part of the structure. A few notes just on detailing. When you're laying out a connection, we do have to watch out for conflicts if we're doing something inside of a tube. Part of that is that the shuriken itself is bigger than a nut. Part of it is that we don't actually detail all that many connections that are in enclosed spaces. So often it's something that the engineer or the detailer may not think about. It has happened to me more than once that, someone will say we need to buy a bunch of shuriken, and I'll just ask out of curiosity what they're doing with it. They'll send a detail, and I'll kind of have to go, I think that's not gonna fit. So definitely something to think about ahead of time. For what it's worth, we do have plugins in both SDS2 and Tekla, the most common detailing software that where you can essentially pick two tubes and apply the shuriken component. It'll put all the materials in there, but it'll also check for these interior conflicts. If you'd like to do it a little more manually, of course, we also have CAD files that we can share that'll help you when you're laying out connections. Aside from that, edge distances need to be aware of. The shuriken themselves, at least the three sizes we have out currently, are all right about 3 inches wide, which means you need 1.5 inches edge distance, which is generally a little bit more than the minimum that the code would require for those size bolts. So again, just something to be aware of as you're laying out the connections. And then lastly, just to give a sense, price and availability. So these we try to price them competitively because at the end of the day, Atlas Tube is an HSS company. The shuriken is really just there to make it easier to work with main product. So you can see the three sizes we have available currently: 3/4 to 1 inch, and 5/8 and 1 1/8 available this coming spring. So just trying to fill out that size range. Obviously, the 1 1/8 works when you have really big loads. The 5/8 is useful if you have a relatively small tube like 4x4, where you don't have a lot of interior space. Obviously, 5/8 is not a very common size in the structural world, but in those smaller connections with less available space, it can come in handy. So with that, I do want to again return to what I said initially. Shuriken is a tool in the toolbox. It does help us solve some problems, reduce field welding, that sort of thing. But it's not the only tool that we can rely on when we do find ourselves in those situations. So just to give some examples here, we have, the hollow bolt from Lindapter, blind bolt from the company Blind Bolt, both, very viable options when you're making one-sided connections. Both of them have, pros and cons compared to a standard bolt. But there are times when these are the right products to use. You know, for example, if you have if you're attaching something to the middle of a 40-foot column, there's no real good way to get in there to install a shuriken, right? So in that case, you really want something that is exclusively from one side. Similarly, if you have a relatively small, lightly loaded attachment, these products are very, very portable at those smaller sizes and will work well with those. So again, just trying to, as much as, of course, I want Shuriken to catch on, I do need to say that there are other options that are appropriated sometimes. So with that, kind of spent a lot of time talking about physical stuff. I want to talk about one last topic, which I do hope will be helpful for you guys, which is the HSS Connections Hub, which is a software package that we've been working on at Atlas 2. Shuriken exists to solve a physical problem with the difficulty of making some HSS connections. And as much as I like to think it's very helpful, that's certainly not the only impediment to making HSS connections easier, both from a design and a construction standpoint. So this is the effort that we're making to try and address that design side of things. So real briefly, big picture, what is the HSS Connections Hub? We call it a hub because we want it to fulfill a number of goals. First of all, we've got a lot of calculators in there that are going to help you design connections. We've also got a lot of typical details. I have been to a lot of engineering offices and been able to see the typical details and not because people don't realize they're important, but because people have deadlines and revising your typical detail sets is not billable time, right? Often those typical detail sets are just going to be details that have been pulled from previous projects. Sometimes they'll include information that's not really relevant, and so to make it easier for people to have access to nice clean sets of details that reflect practices that fabricators are gonna not have trouble building, we went ahead and put those together ourselves and made them available. And then the last part of it is the support, right? If you have issues, we're there to help. And I want to emphasize that this is completely free. So with the Shuriken, I kind of took the time and to make the point that it's not the only thing out there, right? We have to be objective. This part is something of a shameless sales pitch, but it's a pitch for something that's completely free. So again, Atlas Tube is an HSS company. We're not going to change our fortunes dramatically by getting into the software business. The goal here is to make it easier to use the material in the first place. So all of the features, all of the details and the calculators are completely free from the get-go, and they will always be that way. So basically, you enter username, password, and you're in. The goal here, obviously, save time when you're doing design. End up with a connection that a fabricator is not going to complain about. But then also, I think an important thing is that there's an educational goal here, right? I think a lot of engineers, because we spend more time using wide flange in designs, of course, if you have more exposure to something, you're going to get more comfortable with it. And so the goal here is to provide not only an answer, but kind of a procedure to help someone doing this work understand what's happening behind the scenes. So looking at the typical details, we do have showing some of the full sheets. We also have individual files. The goal here is, they're organized by topic. And again, the goal is to make them as fabricator friendly as possible. Aside from the files themselves, which we have, Revit, PDF, CAD, so make it easy to get it into your project. We included engineering commentary with all the details. So you can see here in blue, we have the engineer notes. The goal there is to give maybe some background on when a particular connection is appropriate. What are some design considerations that people may need to take into account. And then also where can they find code references, example calculations, and that sort of thing. Again, to combine the asset with the education for those. The connection calculators, really the meat of the Connections Hub. So right now we have, I believe as of today, there are 48 different connections that we support. Our goal is to get to 72 by the start of NCSCA, which is about 4 weeks from now. At the beginning of the year, we had 0. So we're moving very fast to build this out. And, you know, of course, we're going to get through the ones on the plan now, but to the extent that you think we're missing something, or that one of the calculators has maybe some, you know, there's a feature that would be helpful that's not there, we want to hear from people. That feedback is hugely important as we prioritize, you know, where we're going to put our development effort in the future. Another thing to highlight here is we're not building these ourselves. We're working with calcs.com, which is, you know, an established structural calculator company, formerly ClearCalcs. And so they have, you know, robust existing procedures for quality control and interface and that sort of thing, so that we know that the math is right. We're moving very fast, so admittedly there are, you know, times where maybe, you know, if you look at this, the text and the images might get a little jumbled, that sort of thing. But we are very confident in the, you know, the accuracy of the conclusions. And, you know, again, in talking about how we want this to be not just a production tool, but also, you know, educational tool and something that's completely transparent. It's not interactive at the moment, but you can see there's a little, you have the little caret at each line of the calculation. So basically, every single line, there's a drop down, it has explanations, it has code references, so that a person who's doing this calculation, if they want to understand what's happening, you know, below the hood, all of the information is right there in front of them. And then the last big feature of it is a reporting feature. So essentially, you know, if you're doing this work for a client that wants to have a calculation package, especially if you're doing deferred connection design, I confess, I don't know if that's common in Alaska. It's very common here in New York, less so on the West Coast. But you can quickly export calculation report for the connection. You can go ahead and put your firm's logo on there so that it'll be, you know, as professional and polished as possible. The diagram that comes with the report will be of your actual connection instead of just a generic detail of that connection type. So in terms of, you know, the scale of the members and the number of bolts and all that, it will be, you know, representative. And then again, with every single line of connection, if you know, for example, if we look over here on the rightmost page, every single line has the appropriate code reference so that someone who's really digging in can find out where all these numbers are coming from. So that's the Connections Hub. I have done some presentations in the past where we really, you know, dig in to the specific user interface and that sort of thing. So if you guys are interested in more detail, I'm sure we can you know, potentially work with you to dig into that. Truth be told, you know, structural engineers are pretty familiar with calculators. It's not rocket science to change the number of bolts in a connection, but nonetheless, to the extent there are questions, we're happy to jump in and try to provide that support. So with that, you know, there's the journey and Shuriken and the Connections Hub. I'm gonna kind of stop and open it up to some questions. And again, you know, say really appreciate the time and the opportunity to be here with you guys.
So I've got a question right off the bat. It's Nikolai. So if we had to, sometimes we use A320 bolts in low temperature applications. So
Okay.
if we work on that for an A325, usually is what we detail them to.
Mm-hmm.
It should still work, or would this thing, if it's frozen, would they have to install it when it's not, you know, sub-zero temperatures?
Well, I'm
Yes,
quite yeah. I think it depends on the application. So if it needs to be pre-tension, I would be reluctant to give you any guarantees because we simply haven't done the testing at those super low temperatures. If it's a snug tight application, then it will be fine. I would ask. I assume those fasteners use an extra wide hex nut, the same as an 8563. Is that a fair assumption?
I believe so.
Yeah. So in that case, certainly for snug tight, I mean, really with any of these connections, I did mention the importance of being able to take the torque of pretensioning. Very often that torque is zero, just because friction really does the majority of the work in most cases. Once the plates kind of clamp together, just the way that the nuts are proportioned compared to the width of the bolt, very little of that torque actually gets transferred to the shuriken. But having said that, we understand that in the real world, threads get rusty and plates get greasy and things like that. And so, it is designed to have those factor safeties so that in a condition where things are not optimal and it is transmitting a fair amount of torque, it can take it. So to a certain extent, even at low temperatures, if it were to become, if the brake strength were to go down, friction should still be doing the work for you basically. But as I say, I don't want to be, too overly aggressive in making any guarantees there. But I will say this, admittedly, I think we had talked a while back about doing some low temperature testing, and there was some disruption on our end with our switching manufacturers and that sort of things that kind of never happened. But the fact that you're bringing it up, I agree that that's actually something we should do. It's not terribly difficult to, dunk these in some liquid nitrogen or some dry ice or whatever it is, and see how far we can take them. So, we'll put that back on the development, the R&D calendar.
Do you have any questions?
I looked at the Shuriken. I guess it's a Japanese throwing star.
That's where the name comes from. Yeah, if you look at the shape of the let me put this up here. The shape of the logo. Or you look at it here actually. So this view from below of the 3/4 inch size, that was the first size developed. And that is the logo, and it was because that kind of looks like a throwing star that it got the name Shuriken. I'm sure the fact that I was sitting in Tokyo at the time probably had some subconscious contribution to the choice of name, but that is the story.
Cool.
So
Any
yeah,
questions?
yeah. Sorry, go ahead.
I was just seeing if anybody online had any questions. I don't see any hands raised.
All right, Ted, back to you.
Yeah, no, I was just gonna say, I showed some of these images of the various applications that we've put together, and so I can go ahead, Nikolai. I'm not sure if you have that PDF of the detailed book at the moment, but certainly I can send that out. It's not obviously we tried to make sure that what we were drawing was realistic, but to a certain extent, these exist just to get the imagination going. Because when we realized how much stuff we didn't think of course, it became clear that probably just showing off splices was also leaving a lot of other people maybe unaware of other ways it can be used. So we wanted to just, as I say, get imaginations going with that.
All right. With that, everybody, we'll call the meeting adjourned. Thank you, Ted.
Yeah, thanks for having me.
Much appreciated, sir. Everybody, we have an upcoming presentation, Wednesday, November 19th, discussing snow drifting and ASC 722 with the company RWDI. So we'll look forward to seeing you there. And Ted, thanks again. Have a good day, sir.
Yeah, you too. Thanks again. Have a good one, guys. Bye-bye.